So 2 videos ago, we introduced this disk method for calculating the volume of a 3D object. We took a region, we took an area, we rotated about the x-axis, and we used these steps here to build an integral that would allow us to do that. 1 video ago, we sort of stretched that method out, put it to the test, and we took an area and rotated it about the y-axis. We used the same steps, it just turned out to be a little bit of a different looking integral at the end, involving dy and everything in terms of y. In this video, we're going to rotate regions about any line. So I could take some enclosed area and rotate it about this line if I wanted. That would be the x is equal to negative 1.5 line. Or we could rotate the area about any horizontal line. This would be y is equal to negative 0.75. But again, we use the exact same approach. Carrying out that approach gets a tiny bit harder, and we'll see about that. Alright, so let's rotate the region bounded by these curves about the y is equal to 1 line. Alright, so we'll start by graphing these curves here. So here's my y is equal to sine of x. Remember, pi over 2 is what makes sine become 1. 3.14 divided by 2 is just 1.57, so here's that here, approximately. Pi makes the sine become 0. So here's x is equal to 3.14 and y is equal to 0. And of course the sine of 0 is 0. Your basic sine graph. Y is equal to 1 is just all the points that have a y coordinate of 1. That's going to be this guy right here. X is equal to 0 are all the points that have x coordinates of 0. And x is equal to pi would be this vertical line right here. All the points that have an x coordinate of 3.14. Alright, so what area, what region is enclosed by all these curves? It's going to be this. Alright, now what line do we have to rotate this region about? Well, not the x-axis, not the y-axis. Actually, that same y is equal to 1 line. Alright, so if I imagine taking that area and rotating about that line so that it becomes a solid object, I'm going to get something that looks like this. A weird sideways hourglass looking thing. Alright, same attack strategy as we're used to. Let's visualize this 3D shape as just a bunch of those disks. Alright, so let's try to form the radii of these disks. Well, here are all the radii. On my graph, that would correspond with these lengths right here. Alright, so let's put the math to that. These radii right here, these are vertical lines, which means they're y lines in a sense. So let's use our equation sine of x. But we got to be careful. Let's really walk through what sine of x means, what information, what lines it's giving to us. With sine of x, I plug in the x coordinate of this point, I get the y coordinate of the point. Plug in the x of this guy, get this guy's y. Wait a second. Those are not the lines that I need. I need those red lines, those radii. So this is a bit of a problem. How are we supposed to get those red lines? If the sine of x just gives me these y coordinates when I plug in an x. Here's what you do. Use subtraction. How about let's do this length minus our y coordinate of that sine of x. Notice how that's going to get you those red lines every time. I can do it over here on the right. Here's my length of 1 right here. And I know it's 1 because this is a y is equal to 1 line. So if I take that length of 1 and subtract off of it the y that sine of x is giving us, I will get this little in-between length there, which is exactly what I want. So 1 minus sine of x will give us the r's, the radii of each one of those disks there. Got to be extremely careful when you're rotating a region, an area, about a line that is not the x or y axes. One more time. The length to the y is equal to 1 line, that red line of rotation up there, 1, 1, 1, 1, 1. I've got to subtract the y coordinate, the y coordinate, the y coordinate that sine of x is giving me, and as a result of doing that subtraction, I'll get this in between distance here, which is the r that I need. So it gets kind of tricky. We really got to build, we really got to craft this math together to give us what we know we need. Forming that radius is often the hardest part of these problems. So now that I'm confident that I can plug in an x into this equation, and what comes out is the r of the disk at that x, now I can take each one of these r's, square it, times it by pi. And now I have the area of each one of the disks at that x. And of course, for each one of those areas, I'm going to multiply it by a little bit of height to get the full-on volume of the disk at that x. And looking at that height, I realized that, hey, that's just a little bit of length in the x direction. That's just dx. And now, of course, I can add up all of these little disk volumes to get the total volume of my target shape. Alright, where do I want to start adding these disks? I want to start adding these disks right here. This will be my first disk. Alright, well, I've got to put a x starting bound right here, because remember, this is a dx integral. Alright, so what's the x coordinate of this first disk? Well, x is equal to 0. My last disk is over here, and the x coordinate of that last disk would be x is equal to pi, because that is where we have this intersection. So now that I've built that integral, I can carry it out. Carrying out this integral is a bit difficult. The key is to use the half angle formula for sine to deal with that sine squared of x. But if you carry out that definite integral, the answer you should get is this right here. Alright, let's do another one. Alright, let's sketch my target region bounded by these curves. Here's my y is equal to 1 minus x squared. Just a concave down parabola, shifted up 1 unit. I have my x-axis. And x is equal to 1/2 is just the set of all points that have x coordinates of 1/2, all these guys. So my target region, bounded by all 3 of these curves, this one right here. Alright, what line am I rotating it about? This guy. So if I take this region, rotate it about my x is equal to 1/2 line, I'll get something that looks like a bullet, or maybe a hat. Alright, so I can imagine this 3D volume. Now I've got to imagine that it's made up of a bunch of small disks. Remember, this is the disk method. And actually, we'll learn later how there are other volume calculation methods where you envision that your volume is made up of other shapes that are not disks. And that gets pretty interesting. We'll look at that in the future. Alright, got that? So let's start building these disks. Let's try to form their radii. Alright, radii. This guy's radius. Alright? Looks like that radius is actually getting bigger as we go down. Just a little observation right there. Alright, let's see if we can locate that on our graph though. So here are the radii of the bigger disks, and the disks get smaller as we go up. Alright, I see those radii. Let's see if I can bring the math to give me the lengths of those radii. Well, my first thought is this equation right here. But let's just verify what it's actually telling us. Alright, I plug in an x, and I get the y of that point. I plug in an x, and I get the y of that point. Alright, this equation's giving me y's. Those are not in the right direction. So I'm thinking that I definitely gotta switch this guy up. These red lines, these radii, are definitely x lengths, x lines. So I'm gonna have to flip this equation so that I put in y, do some math, and it gives me x. So I'm just gonna get x by itself. I'll move x to the left. Alright, now I'll move y to the right, so I'll subtract y on both sides. Okay. Now x is not completely by itself, so I'll take the square root here. Gotta be careful, whenever you take the square root, two things pop out. I have a plus form of this equation and a minus form of this equation. So you have to be careful. I'm only concerned with the plus form of this equation. Why? Well, I just want x lengths that are in this direction. These are positive x's. And if I continued our little parabola here, these x coordinates over here are the negative x coordinates, the negative x's. And I'm not concerned with those. So I'm just going to drop the negative and just use the positive form of this x equation. I'm literally just going to ignore the negative half of it. Math is a tool for us to craft. Let's just use what math we need. Alright, so I'm here with this equation. Let's focus on this guy real quick. So I have this equation here, but I still have to be careful. Does it give me those radii? Well, let's see what this equation is telling us. It allows me to plug in the y coordinate of one of the points on this line, and it gives me the x coordinate of that point. Plug in the y coordinate, gives me an x coordinate. Plug in the y coordinate of the point, gives me an x coordinate. Alright, those are definitely not the radii that I need. Looks like our job's still not done here. Gotta throw some more math in there to get those red lines. Gotta be a bit clever. Plug in a y, I get the x of that point. Maybe I can do another subtraction like I did in the last example. Take the x length that we just got from that equation, subtract this blue length, whose length is 1/2. Alright, that'll get us that red line. Let's try somewhere else. If I plug in the y of this point, I'll get this guy's x. Alright, subtract that 1/2. The remainder will be that red line, that radius that I need. So I'm going to take these x lengths coming out of this equation and subtract each one of them by 1/2. That'll be the r that I need. So tricky stuff. So for this equation here, now when I plug in a y, what we've programmed our math to do is give us this length. So we're good. So for each one of these lengths, since it's our radius, I want to square it and multiply it by pi. So now for this equation, when I plug in a y, I get the area of the disk at that y. I get one of these every time I plug in a y. How do we promote this area to being a volume? Well, I just got to multiply by a little bit of height to get the volume of the disk. Well, this height for us, that's a little bit of vertical line. That is going to be a dy. So I need to take each one of our areas that this equation is giving me, multiply it by dy. Now when I plug in a y, I get the disk volume at that y. And finally, I want to add up all of these disk volumes to get my total shape. Alright, the bounds. Where do I want to start adding these disks? Well, I want to start here. Now you might be wondering, well, why don't you want to start here? Well, this is a dy integral. The lower bound has to be the smaller y. So this is the smaller y right here. This guy will be the bigger y, and therefore it will be our ending bound, our upper bound. Alright, so what is the y coordinate of this starting location? And that looks like y is equal to 0 to me. My last disk is going to be right here. What is the y of this? Well, that's actually a good question. this point right here is on our green curve. I want to figure out the y at this point. Well, that point is at an x-coordinate of 1/2. So all I got to do is plug in 1/2 into this equation and see what y comes out. That is the y-coordinate of this point right here. Yeah, so it's always tricky. This chapter of calculus is really about crafting and being clever with your math and really being able to visualize it, what sort of lines and distances each equation is giving you. So if I do that math, I'll get that the y is 3/4, 0.75, and that will be where I want to stop. My last disk, the smallest one, will be there. Alright, our integral is finally complete. If you were to carry out this definite integral, the final answer you would get 7 pi over 96. Alright, that's it for this video. We have rotated now a region about the x-axis, the y-axis, but now you should be comfortable rotating a region about any axis, any line. And again, it's just the same procedure we've been working off of. It just gets a little complicated, especially when you have to form those radii. If you want some more practice, I'll have a practice video where we go through a whole bunch of different problems using the disk method.